Hiya, it's Mr. Baker with another physics video. Today we're going to be evaluating nuclear power. We're going to be looking at nuclear issues. So we're going to be looking at nuclear issues today. You are going to be able to have an opinion at the end of this about whether we should plan to use more or less nuclear power in the future. Okay, so let's start off by reminding ourselves about the dangers of nuclear radiation and start off by looking at something called background radiation. Now, background radiation is ionizing radiation from radioactive sources that are in the environment. So examples might include rocks and buildings. That's the rock, not a building, although he's solid as a building. He's the rock. Soil. Now, the rocks are in the ground. That's some soil, if you weren't sure what soil looked like. And so because rocks are in the ground, then soil can also be a background radiation source. And we grow stuff in the ground and then we eat it. So bananas have radiation. Most things that we eat have a little bit of nuclear radiation in them. Walnuts apparently have quite a lot of nuclear radiation as well. And because we eat stuff that has got nuclear radiation, we give off nuclear radiation. So living things like us and cute little puppies also will be a source of background radiation. Cosmic rays are charged particles, nuclear radiation that comes from stars. So nuclear radiation that's come from the sun will come towards us and be deflected by our magnetic field, but some of it will actually be absorbed by the atmosphere. Some of it will get to us, and we'll look at how that will be dangerous maybe for different people that do different jobs. Like people that are pilots, because they're higher up in the atmosphere, not as many of the cosmic rays are absorbed, and so because of this you might absorb more background radiation if you are constantly travelling by air. Lots of medical uses. We looked at gamma knife treatment before, and other treatments which use nuclear radiation are a source of background radiation. Nuclear power stations, in nuclear fission, some of the waste products and even some in the reactions will cause radiation. In nuclear weapons testing, that will give off nuclear radiation which will hang around for a little bit afterwards. And radioactivity in the air, so radon gas. So things like some rocks, igneous rocks, that might have some kind of radioactivity. So granite, for example, now down here in Devon, where some buildings will be built of granite in the rocks, that's giving off potentially radon gas, and that is a source of background radiation that you've got to be aware of, especially if you live in a house that's made of granite. So where does background radiation come from then? So we've looked at all those different things, and you can see all these different doses now. In the GCSE, what you will have to be able to do is to look at pie charts, maybe like this, or tables like this, and then you have to be able to compare the different doses that are given by different things. So here you can see that the source that is giving off the most radiation in millisieverts is the natural radioactivity that is in the air. Medical applications, 332, are the same as what ground and buildings would give off. So you've got to be able to compare the different sources of background radiation and then talk about the different threats and risks that might be involved in that. The larger the dose of radiation, the higher the risk of cancer. High doses kill living cells, and smaller doses carry less risk, but the risk is never zero. Because of background radiation, we are all potentially absorbing some ionizing radiation all of the time. So let's remind ourselves again of the dangers of alpha, beta and gamma, the types of radiation that we've been looking at. So the danger of nuclear radiation depends on three things, remember: the half-life, the ionizing ability and the penetrating power. So let's compare that for alpha, beta and gamma. Now the half-life will depend on the source. The shorter the half-life, the less risk. The longer the half-life, the more risk there is. The ionizing ability is the ability of this radiation to change things into charged particles. Alpha is very good at this, it's got a high ionizing ability, then beta, and then gamma has got a low ionizing ability. Now the higher the ionizing ability, then the more likely it is to cause charged particles to form, and if that's happening inside the cells in our body, then that can kill off the cells in our body, and that can also cause cancer potentially as well. You've got to balance that with the penetrating power. How able are they to go through different materials? Now alpha has got a very short range in air. It'll go maybe a couple of centimeters and it'll get stopped by our skin, by a piece of paper. Beta has got a medium penetrating power, so it can go through our body, but it can get stopped by foil, aluminium foil. And gamma has got a high penetrating power, but it's got a low ionizing ability. So then how dangerous are they? So alpha inside the body is very dangerous because it can be absorbed by the surrounding tissue. But alpha outside the body only causes some danger. It can be absorbed by skin and retinal cells, but it can't get through the skin, so it doesn't cause so much of a risk. Beta and gamma are both dangerous, and they can reach cells throughout the body because of their higher penetrating power. So why is nuclear radiation dangerous? So when alpha, beta and gamma get absorbed by atoms, they will get absorbed by the electrons, and then the electrons will be lost from that atom, causing it to charge up. If that happens inside a cell inside our body, if that happens inside the DNA, inside the nucleus, then it can change what that cell does, and it could potentially cause it to reproduce. If that happens, then it can cause a cancerous tumour. So let's have a look at this in terms of nuclear power stations. For nuclear fission to happen, there's going to be some nuclear waste. After being used, fuel rods are very hot and very radioactive. They are stored in water for 200 days to let the radioactivity die away and to cool down. So the picture on the right here shows one of the world's largest sites for reprocessing radioactive waste, which is The Hague in France. So the nuclear waste is cooled further before being reprocessed, and this is a process where unused plutonium and uranium are removed to be used again. The waste is mixed with molten glass and then stored safely far below the Earth's surface. Now this has potential risks. If the radioactivity were to leak and go into water supplies, then that could cause contamination to those water supplies. So that's a potential downfall of storing nuclear waste. We've got to also store this nuclear waste for potentially thousands of years. So this picture on the right are the doors to the Chernobyl power plant. In 1986, a nuclear power plant in Ukraine exploded. Many thousands of people were affected all over Europe, and many suffered and died of associated disease and cancers. In 2011, a natural disaster caused nuclear reactors in Fukushima, Japan to fail. The failings could have been stopped if safety procedures had been followed properly. People within 20 kilometres were evacuated and surrounding water was contaminated. There have been some deaths and related cancers reported. So nuclear accidents are rare, but when they have occurred, they have had a large and lasting impact on communities and the rest of the world. So these are the things you should be able to do then after this lesson. You should be able to identify sources of background radiation. You should be able to compare the risks and damage associated with types of radiation. You should be able to describe the risk of nuclear disasters. And you should be able to describe how nuclear waste can be stored or disposed of. So at the beginning of the lesson, we asked this question: should we plan to use more or less nuclear power in the future? So this is really evaluating all the advantages and all the disadvantages of nuclear power stations. And you'll want to make up your own mind on this. So some of the advantages of nuclear power is that for 1 kilogram of uranium, we get the same amount of energy as if we had 2 million kilograms of coal. So nuclear power is going to last for thousands and thousands of years. Another advantage is once the power stations have been made, they don't release any carbon dioxide, so they don't release any greenhouse gases. So that's another major advantage. Nuclear power has got the potential to provide all of our electricity needs as well, and it's very, very reliable. So there's lots of advantages to nuclear power. But as today we've seen, some of the disadvantages are that there is nuclear waste, which has got to be stored for thousands of years. And if that leaks and contaminates water supplies, then that could be dangerous. And power stations do sometimes go wrong. So we looked at 2 examples of Chernobyl and Fukushima, and both of these disasters have had massive impacts on the communities around them and on the world. So it's up to you really to make up your own mind whether you think that we should have more nuclear power stations or not in the future. It's one of these things that you might have to write a longer answer question on potentially. So should we plan to use more or less nuclear power in the future? Well, that's for you to decide. Okay, so I've been Mr. Baker. This has been another physics video, and I will see you next time.